Welcome to this worked example. Today we're going to have a look at a rocket booster which returns from space. And the question is, at what height should the booster start firing again to make sure it lands safely? Well, you might think that the work that needs to be done is simple. It's simply the energy it has right now, saying it's mgh. It's potential energy. That's all the energy that needs to be dissipated, so that's easy. Well, then you would not take into consideration that the rocket is moving downwards. And when the rocket is moving downwards, it experiences air friction, or air drag. And the air drag is in the opposite direction and is moving upwards. So the air drag is actually slowing down the rocket, is actually performing work on the rocket. So what do we need to calculate at what height the rocket should start firing? Well, we need its terminal velocity. How we're going to obtain that terminal velocity? Well, it's actually quite simple. We can equate the gravity to the air friction. So this would be mg, and the air friction is known as half times rho, the air density, times a, the frontal area of the rocket, times this coefficient times the velocity squared. Okay, in this equation, this v is the terminal velocity. So we want to free up that variable. And here we actually divide it by a half. That's the same as putting this 2 on top. Okay, then we still need the velocity, which is the square root of okay, so now we know what the terminal velocity is. Next up, we're going to set up an energy balance, which is going to take the work which is done by the rocket, which can be described as, well, the work is equal to the force times the distance over which the force is applied. And we're going to take the work done by the rocket into consideration with its end velocity and its initial potential energy. So what we're going to say is that the final speed squared plus the work done by the rocket, which would be F, the force of the rocket, which is the thrust, times the height at which it starts firing. And we're going to say this is equal to the initial speed squared plus the potential energy of the booster. Okay, so we want this height. Because we want to know at what height the rocket should start firing. So we're going to say that this is equal to this. So we have now that the work done minus the potential energy of the rocket is equal to the kinetic energy in its initial state minus the kinetic energy of its final state. Then you can separate the h out of it. And right here we have half m, which we can separate out of it, minus the final squared. Okay, so now we can simply say that h is equal to half m times the initial velocity squared minus the final velocity squared divided by this term here, which would be f minus mg. Okay. So let's fill in some numbers. If we were to fill in the velocity, which would be the terminal velocity, then the initial velocity, by the way, is the terminal velocity. But if we were to fill in the values for the terminal velocity, we would find a terminal velocity, Vt, is equal to 566 meters per second. And if you know the terminal velocity and we know the other values in this equation, we find that we have a final height of 17.4 kilometers. So this height was calculated with a final velocity of near zero. We're going to simply say that the final velocity was around 5 meters per second. What is important to realize is that the rocket's initial height and initial speed actually don't matter, because above the height of 17.4 kilometers, the rocket simply travels at its terminal velocity. If it goes quicker, then the air friction gets higher and or larger and slows down the rocket even further. So this is what we've calculated. At this height, the rocket should start firing a thruster to make sure it lands at a safe speed, which it hopefully won't explode. So thank you very much for watching this example.